Hi, welcome to another Hopper on 6502 video. I'm still in my BIOS, my 8K BIOS. Let's reset this here if I can find this button. There we go. So I'm still on my 8K BIOS. So I've got almost 56K of RAM. I've got a file storage here of 64K. So I've got a disk, essentially file storage. And in my last episode, I was talking about my C compiler and how it sort of failed me. So I've got a C compiler that is self-hosted on the 6502 machine, so the compiler is running on the machine. But it's too big. It's about 25K, which when you've only got 64K of file storage and only 56K of RAM, it's too big. So it's compiling using an abstract syntax tree, which chews up too much RAM, so you can't compile very big programs with it. And when it compiles, it makes programs that are too large. They're pretty fast. It's just too big for the machine. So that got me thinking, what would be the ideal solution for a 6502? So let's go have a look. So I decided to try to build a virtual machine on the 6502. It's not my first virtual machine. The Hopper virtual machine runs the Hopper language on it. So I've got a fair amount of experience with virtual machines on the 6502. But one of the things that goes wrong first with a virtual machine, and virtual machines always tend to, well, more often than not, with a few rare exceptions, tend to be stack-based. The 6502 machine stack is very limited. It's got an 8-bit stack pointer. It's only got 256 bytes of stack. So if you're trying to build any kind of reasonable language using the machine stack, it's a bit limiting. So you end up building a parallel stack, and for each stack operation, you've got like 6 to 8 machine instructions, which immediately you're going to have a slow virtual machine. So I was thinking, how do I make it so that I can use the hardware stack, right? So no like synthesized stack, use the hardware stack, right? And yeah, that's limiting. And a lot of these things are limiting, but I wanted to see how I could come up with the fastest possible virtual machine on the 6502, and I've done a pretty good job. Page-aligned functions. So each function has to be less than 256 bytes long, and it has to be page-aligned. In other words, not page-aligned, it just mustn't cross a page boundary. So you can have two small functions on the same page. They just can't cross a page boundary. And if you do that, you can use one of the 8-bit index registers as your program counter. And when you call a different function, no problem. You're jumping into, like, think of it like a code segment, and each function is in its own segment, and the segment is 256 bytes. Only 128 opcodes. So again, page limits are quite fundamental to the 6502, like a 256 byte page limit. So if I have even numbered opcodes, I can have 128 opcodes, which means I can have all their addresses in a single 256 byte page, which means my jump table fits into a page, which means it can be indexed again, using an 8-bit register, so the X register, for example. So stack pointer here, Y register for the program counter, X register being used a lot for indexing. I use it for the BIOS calls, and I use it for the jump table for the opcodes. Simple types. So in my first iteration, I haven't really done anything other than value types. So no like lists or dictionaries or strings. I've got strings, but they're immutable string constants, which is the same as what I did in C. You actually get away with a lot just doing that. And then BIOS integration, taking advantage of the BIOS functionality inside the 8K BIOS that's on this machine already, which gives us a heap, it gives us a floating point library, it gives us a 32-bit long library, it gives us the file storage, bunch of other things. Memory model, registers, yeah. So global variables, Again, I limit them to one page, so you can have one page of global variables. And you can have as many constants as you like. So as many, you can define great big tables of arrays of constants, so like fonts and things. There's no limit on that. Anyhow, let's get back to the beast. So by way of example, okay, so there's the obvious Blink program running here. There we go. So you can see that it's actually running on the hardware. So, and then I've got Control C, so that'll break. And if we look at the source for this, type blink.vma is my virtual machine assembly. So what I've done is I've defined opcodes and an assembly file format here. So at the top of the file, it's got constants, so you can name your 0-page slots, and you can put dots inside the names. So like Hopper used them for namespaces, but it means I could use the same names. So these are BIOS call IDs, 0-page locations, that sort of thing. Data is kind of where you'd put string constants, so you've got a data segment. And then your first function, your entry function, is called main, and then the others can be named. So the others go .func and the name. And there we go. We enter our function, and these pushes and pops it's a stack-based virtual machine. So set up the arguments to call pin mode to for my LED to put it into write mode, and then here pin 0 output mode. Turn it on with a 1. Oh, that's the pin mode here, and then here is high. Turn it on, and it's sort of got synthetic ways of doing the A and Y register because these BIOS calls use the registers. So you can say load. Push 0 onto the stack and then pop it into the A register. Push 1 onto the stack and pop it into the Y register. And then call pin write. And those are the arguments it's expecting. And it's sort of synthesizing the registers. They're not really the registers because obviously the Y register is a program counter. There we go. And then we call delay in the, we've got time APIs in the BIOS. We call delay. I check for break, which is either the Control C or I've got on my board, I've got an NMI button here, non-maskable interrupt will also break. And if there's a break, I branch out of here to exit. I've still got, I don't patch labels yet, so that should be the exit label and it should be patched. So backward jumps work fine, so branch to loop here works fine because it's already defined by the time I use it. But for labels that aren't defined yet, I haven't done a patch up table yet. But I will. Anyway, and then it branches back, and so it does a break. It's actually doing it. It should have alternated, but it's delay, break, check, turn it off, delay, break, check, go back again, turn it on, etc. So this is your assembly language, and you can edit it on the machine because I've got my editor that I started this whole thing with. So here's your full screen editor, 25 by 8 actually. And F1 tells you what the keys are for the editor. There you go. So you can edit here, and then when you've finished editing, you compile it with virtual machine assembler, Blink, and then once you've compiled it, you end up with a executable called blink.bin. And I've made it so that if you just type Blink, it'll execute it. But the magic behind that is actually it's using another executable called VM, the virtual machine. And I'd like to try and keep the virtual machine under 2K, so it's super tiny. So you've got you've got about 50K of RAM if you're running one of these programs in the virtual machines. So what's actually happening behind the scenes is it's running the virtual machine with Blink as an argument is how it's working. So the BIOS has been extended so that it knows how to deal with bin files. It launches them using VM. And the assembler itself is still pretty small. It's still under 5K. And the memory use while it's compiling, it's got a hell of a lot more than the C compiler. Okay, next program. I've been using Noel's Retrolab benchmark as my benchmark here so I've got a C version. So this was the version I wrote in C. So if I compile it with the C compiler, we can see the problem immediately. It's only got 23K of memory free. Compiling this, it took 6K of memory because of the AST to compile this. So very expensive. And it created a file that was 839 bytes. It's pretty fast. So let's do that and see how fast it is. So 417 milliseconds to do the benchmark, right? Now by comparison, if we do VASM of null, so this is the virtual machine assembly version of it, is a lot more free memory. So it uses a lot less memory to compile, and this is not linear. It uses about 3K. So you can, as your program gets bigger, it increases very slowly. So we can compile much bigger programs now on the 6502 using this assembler. And then if I run it, okay, so 593 milliseconds versus 417 milliseconds. This is compiled to native code. This is running on a virtual machine. So I'm pretty happy with that performance. And I've got another version on this machine. I've got a hand-coded assembler version, fastest possible version. And this is the fastest I can imagine seeing it run with hand-coded assembly on this machine. So the virtual machine is only running at half the speed of the fastest possible time. So compared to the Hopper virtual machine, this is incredibly fast. But that's not the kicker. Let's have a look at the hand-coded one. So this is, typo. This is the hand-coded one. So you can get an idea of how much code there is in it. The C version is quite big, so let's have a look at that. Hex dump null c.exe. Quite a lot bigger. So that's what the C1 compiled to. It's pretty fast, but it's just generating way too big binary. And then part of the point of this virtual machine was to increase the code density. So for each virtual machine instruction is the equivalent of 10 machine instructions. So you can in theory you're going to end up with smaller programs. So let's see if that's true. So if we go and look at null.bin, there you go. So this is the virtual machine version. And if we want the numbers, so the virtual machine version 199 bytes. The C version 407 bytes. Oh no, that's the source code. 839 bytes. So this is 4 times the density of the C version already. And it's twice the density of the hand-coded super fast one. So it's only 200 bytes. So what do we got? We've got a virtual machine that's only running at, it's running already without much optimization, running at half the speed of hand-coded assembler. So pretty darn fast. And it's making small programs. And the compiler, so if I compile hello world, is using it's not using that much memory, which means we can compile bigger programs. And smaller programs means we can fit more on this storage disk as well. Let's have a look at how hello world looks like. That's what hello world looks like. Let's look at the hex. Not very much. And then let's run it. There you go. So what does hello world do? It's got some constants to use my 0-page argument for the string API. This is the ID of the string API in the BIOS, and there's the string. So this D here is push data. So push from the data by this address onto the stack. So it pushes the address of this onto the stack. Pop it into the 0-page variable str, which is what print string takes as its argument, and then just call print string, and then halt. And yeah, halt is actually return. Clean up the heap and return to the BIOS with a clean exit. So that's it. That's the hello world in this assembly format. So what have I got now? I've got an assembler, and I've got the thing that runs the code that the assembler generates, which is the binary. So it's the start of a tool chain, and what I hope to do is chain them together, as opposed to having one big monolithic tool like the C compiler included the optimizer in the compiler, and I ended up with a 25K C compiler. Whereas a chain of little programs is much better. So after this assembler, the next thing in the chain should be an optimizer. So to optimize, to do obvious optimizations of the code, convert long jumps to short jumps, that sort of thing. And then on the other end of the tool chain, I can make a high-level language compiler that generates this assembler instead of generates this instead of generating native code. And in fact, that's probably where the optimizer should be. It should be at this level when you're in bytecodes like this, when you're in opcodes. So before you send it through the assembler, just optimize it. Yeah. Anyway, that's sort of the gist of what I've been working on. So I've got two tools in my sort of compact tool chain that's going to run on the device. That's how far I've got so far. And I'm going to do a little bit of a walkthrough of how the VM works inside, and it's kind of interesting. I'm just going to pause quickly so I can get that screen up. Okay, like I said, there's two programs. There's an interesting thing I forgot to mention. The programs that you need on this, you obviously need the 8K ROM. That's, this little ROM here. So you need the hex for that ROM. And then once you've got that, there's the editor. The C compiler is kind of handy because tools like hexdump and type and captures how I very quickly transfer source code from my desktop machine to this machine. These are all written in C, so it's nice to have the C compiler so you can compile them. And then there's the assembler, and there's the virtual machine. I'll put a link on GitHub to the hexes of these, so you don't even have to compile them. You can just burn the first one, the BIOS, onto the 8K, and then for the rest you just use this as part of the BIOS. There's a hex command, and you can just upload them and get them onto the storage. So if you have one of these machines, the only tool you're going to need is a serial console, like I'm using PuTTY here, like a regular serial console, BT100 emulation. So yeah, you don't even have to build any of it, and of course it all works on Linux because you just need a serial emulator. I mean a terminal emulator. All right, let's go have a look at the source code. So there's two tools. There's the assembler. So this is the assembler. It's, what I say, 4 or 5K, but the error messages are nice and verbose because I was kind of like, the error messages for the C compiler were very cryptic, and I was tired of that. So I decided I'll worry about it later and just make them big and verbose. And then if I need to make them smaller in future, I can. So these are all applets that run on the BIOS. So they've all got the little, well, actually, if you go and look in the definitions here, they're Hopper BIOS applets, so they get built accordingly by my assembler. All right, and then the more interesting one is the VM. This is all written in Hopper. This is all Hopper assembly. And interesting part of the VM, I added some functionality to the Hopper assembler. I cheated a bit. So what I did, this is a very common thing, is to want to have a jump table. And the jump table is often based on some ID. And that ID might as well be in an enumeration type. So these are your opcodes in your enumeration type. And they're very much what you'd expect, like from typical stack-based machine opcodes, pushes and pops, numeric operations that use things off the stack. And then in addition to that, I've got some special instructions, like I've got global push and pops, which are, to the bottom. I've got a global page, a 256 byte global page. I did this so that I can double the size of the amount of variables you can have, because you're limited by the stack in a stack machine, and you've only got a 256 byte stack. So local variables are in your stack frame when you call into a function. So having the globals in their own page double the amount available. Functions specific to the data operations, and then these are 0-page specific functions. So you've got push and pops that work with a 1 byte offset to push and pop from the 0 page. And the convention here is B for a byte, W for a word, and Q for a quad byte, which is a 32-bit byte. And because we're using the 32-bit math library in the BIOS, these are useful APIs to have. Even if you're working with 2-byte integers, you're still going to use, print it to screen, print me an integer. It'll use that function. And then things to enter and leave functions, set up the stack frame as you enter and leave a function. Anyway, so what I was saying is I created an enumeration, and then I did this. Created sort of a uninitialized array constant, which is my jump table. And the Hopper assembler looks at that and goes, well, because you're supposed to put an initializer here, you're supposed to say equals and then, initialize this with some values. So if you don't, the Hopper assembler now just assumes that you're building a jump table. If two things are true, you didn't initialize it, and the type of the elements of the array are these is an enumeration type. And so what it does is it just creates a 256 byte chunk for this that's empty. And then later during compilation, if it encounters some of your enumeration type names as labels, it resolves that label into the jump table automatically. So this jump table is built automatically simply because I used an enumeration, and the members of the enumeration are the same as the names of my labels. And you can qualify them too, so you can avoid clashes like namespaces. You can put the dot in, the name, the opcode type, and the dot. And then here's me using the jump table here. You just that was the same name as the constant thing at the top, so you just jump to it. So the way my virtual machine works is it comes in here the first time and executes the no-op instruction, because it comes in here with y at the beginning of a function with y is the program counter as 0, and it comes into no-op. And what does no-op do? No-op does a tail call to the next instruction. All these instructions do that at the end of what they've done. Like this, it's going to push A onto the stack, which is something called A store, or pop it off. Pop something off the stack and store it in the A store. And so this here is the opcode, and then the next 4 lines is execute the next instruction. So when it comes in, the first thing it does is execute the next instruction, which is load the instruction from the program counter in the code page and jump to it. So that'll be one of these, it'll jump to something. Yeah, so that's how they work. Yeah, some of them are sneaky, like pushing a word is very similar to pushing a byte. So it pushes the first byte and then falls through and pushes the next byte and then executes the next instruction. So it's not that many cycles per instruction to thread to the next instruction. So it's this threaded interpreter of just jumping from the one to the other. And this is just one big function with all these opcodes implemented like this. So using the machine stack as my virtual machine stack, and using Y as my program counter, and then using X for everything else. Like whenever I need something else, I use X. So occasionally I have to protect Y. So if we look at the syscall, when I call the BIOS call, I have to push and pop Y. And I just assume that A is always going to get munted. And then there's another version of, this is the fast version of syscall, syscall X, so syscall express. But if you're calling a syscall that requires A or Y register as arguments, or it requires you to be aware of the return value of the flags, then you should call this one, which is slightly slower. So that's how it works. There you go. Yeah, pretty neat. So this amount of code here makes your virtual machine that can execute code at a speed that is only half the speed of like hand-coded as fast as possible. So way faster than I imagined. And what are we talking about in terms of constraints? The biggest constraint is these 256 byte limits. So you've only got 256 byte stack, and your maximum function size is 256 bytes. But remember that it's quite high density, because let's assume each instruction has a 1 byte argument. That's 128 instructions. But that's the equivalent of about 1,000 machine instructions, which is the limit of your function size. And then of course you're limited to 256 functions, but you don't have that much RAM. Well, they don't have to fill a full page. They can be like little functions that fill part of a page. It's just that you can't put a function across a page boundary, because then you can't just increment the program counter with one instruction like that. It never has to check if it's overflowed or not. And it also means that all your jumps, all your branches are always within the same page. So all your branches are 8 bits or less. And I was pretty sneaky with that, because normally with branches you use a signed. See if I can find them. Here we go. Here's some branches. Normally with branches you use a signed offset to add to the current program counter, to branch forwards or backwards. So branch. This is branch if not 0. So if the top of the stack is not 0, then branch. And what I did is I made two functions. I've got branch if not 0 backwards and branch if not 0 forwards, which means I didn't have to use a signed offset. I can use an unsigned offset, which means I can use a byte to cover the entire range of 256 bytes of your function. You can jump all the way from the end of your function all the way to the beginning with 1 byte instead of needing a 2 byte integer. So instead of having a branch not 0 byte and a branch not 0 word for the longer ones, I just said branch not 0 backwards and branch not 0 forwards, and so there'll always be short branches. So yeah, pretty sneaky. Anyhow, if you're interested, and if you've got some feedback in telling me how I could make, what's wrong with my virtual machine, how can it be faster, and the two things we want is we want a faster virtual machine, faster execution, and we want smaller code. And smaller memory use as well, so runtime RAM use, and this uses very little. So you want to reduce your memory footprint, you want to reduce your absolute code size footprint, and you want it to be really, really fast. So tell me what I did wrong, tell me what you think could be better. I'll put links to the source code, I'll put a link to this function, to this file, so you can go and have a look at this. Tell me how I can make these opcodes more efficient. And if you're interested, ask for an invite to the Discord, and you can join us on a Discord server to chat a bit more about it. So, thank you for watching.